Hello and welcome back to your Chem 4 lecture. We are on lecture 8 now, and that means that we are wrapping up chapter 4 today. And in lecture 8, what we're going to do is we're going to talk all about the electronic configuration of atoms. So far, when we've learned about the atoms, we know the neutrons and protons are in a very small central place in the atom called the nucleus. And so far, all we've said is that the electrons kind of surround them in a cloud. While there's some structure to that cloud that we're going to learn about, and we're going to touch on that briefly to explain why we have these certain trends on the periodic table. So today we're going to understand the electronic structure of atoms, and then follow that up by understanding the trends that we see on the periodic table, both left to right and top to bottom. Okay, but before we do that, we have to introduce something that you're familiar with, which is light. So light is a form of what we call electromagnetic radiation. And electromagnetic radiation incorporates a huge spectrum of electromagnetic waves. Now, like you could spend a whole physics course, talking about electromagnetic radiation, but we just have a few slides here to understand it. The idea is basically an electromagnetic wave is a self-propagating electric and magnetic field. Basically, the electric field goes one direction, the magnetic field is orthogonal to it, and it acts like a wave as it goes through. So we'll take a look at a few different forms of it, but the electromagnetic spectrum incorporates everything from visible light that we can see to radio waves, which are very long waves, microwaves, X-rays, gamma rays, ultraviolet rays, infrared rays, all of that is incorporated into the electromagnetic spectrum. And yeah, these are waves that also behave as particles. Again, you could spend a whole semester talking about this, so we just have to hit it very briefly. The particles are called photons, but they also behave as waves. It's this weird fundamental property of matter that as it goes smaller and smaller, the more matter behaves as a wave, even though it can be a particle at the same time. Again, not within the scope of this course. So just real quick, a wave, we'll just look at the structure of a wave real quick. I'm going to talk about wavelengths. It's like the distance between the peaks of the waves. So if a wave looks like this, hello, there we go, oops. So if that's a wave, then a wavelength is going to be the distance between the peaks or the distance between the troughs here. And that's what the wavelength looks like there. So electromagnetic radiation that has a lot of energy has very short wavelengths. So it would look like this. Yeah, you get the idea. And low energy radiation has longer wavelengths. So that's like that. So hopefully you get the idea. This is like a sinusoidal wave, if you're familiar from your math classes. Classic wave behavior, we're not going to dive into it any farther than that. Here's our electromagnetic spectrum. So they start from very long wavelengths on the left, which include things like radio waves. As we move to shorter wavelengths and higher energy, we go from radio waves to microwaves to infrared. And one thing that we can note here is that radio waves, for example, which also include TV waves and cell phone waves, which are maybe considered microwaves, it's kind of in between there. Notice that these radio waves are passing through us at all times, right? We don't feel it when we turn on a radio. So that suggests something that it's very low energy, right? If it were high energy, we would expect to feel it, absorb it, and feel it. So radio waves, very low energy, and they have long wavelengths. As we move into microwaves, now a microwave oven itself, of course, if we put our hand in there, if we were able to put our hand in there and turn it on, we would definitely feel it, right? Because the water is going to absorb those microwaves. That's because that microwave is using a tremendous amount of that in a very contained space. And it happens to be the right frequency that water absorbs. So it makes the water molecules excited, which makes them move faster, which increases the temperature of anything that has water in it. Yeah, satellite TV is what it's talking about here. Now, infrared, all of a sudden now, when we get to infrared, that's actually radiation that we can feel. Infrared is basically when you're standing away from a fire, you hold your hands out like this, you're feeling heat enter into your hands. That's infrared radiation. You can't see it, but it's being emitted by the fire or whatever heat source you have to have as heat. Then finally, we get to the very narrow band of what we call visible light. So visible light, like Roy G. Biv, right? So red, orange, yellow, green, blue, indigo, violet, all the way over here. This is sort of where we normally think of light, but light itself is just like a very small slice of radiation, as you can see, which extends from very long wavelengths all the way to very short wavelengths. So just to give you an idea here, wavelengths of electromagnetic waves go from about 10 to the 6th meters all the way down to 10 to the negative 11th meters. And the visible light that we can see accounts for only about 300 nanometers differently, from 400 to 750, I want to say, is kind of what we can see. So it's a very narrow range that we can actually see. Moving up to shorter wavelengths, higher energy, we have ultraviolet light and X-rays. So ultraviolet light, you may be familiar, that's what comes off the sun and can give you a sunburn, for example. That's why you wear sunglasses to help cut down on UV entering your eyes, which are very sensitive, of course. X-rays, you're familiar with, your bones absorb X-rays. So that's why we can image bones using X-rays. We shoot X-rays through a patient and see what comes out the other side. Any X-rays that are absorbed are places where bone has been hit. And then gamma rays, which are extremely dangerous. These can come from mostly cosmic sources. So there's certain events where like a black hole ripping open a star, for example, will produce a tremendous amount of gamma rays. Supposedly our sun itself, it does produce gamma rays, at a pretty constant rate. Supposedly there's processes that can happen in the sun that produce a tremendous amount of gamma rays and like a gamma ray burst. And, theoretically that could, extinguish life on Earth because they're extremely dangerous. Anyways, going beyond it here, just kind of showing you here, visible light is just a tiny part of this spectrum here. And again, we go from low energy over here to high energy over here. So let's go ahead, let's do a quick learning check, keeping in mind, this is our little diagram here. Identify which form of electromagnetic radiation has greater energy, yellow or blue light, ultraviolet or infrared, and X-rays or microwaves. Go ahead, pause, take a look at the diagram and see if you can identify which one's higher energy. Well, hopefully you got it right. So blue light is a shorter wavelength than yellow light, so it's higher energy. Same thing with UV. UV is higher energy than visible light, which is higher energy than infrared light. And then finally, microwaves are very low energy light, and X-rays are very high energy light. Okay, so that's electromagnetic waves. Now, the reason that we explain that is so that we can explain a particular phenomenon of elements that people discovered a long time ago. So this is one of the original ways that people were able to identify elements is you take a pure sample of an element, or it can be a mixture as well, but with a mixture, you're going to have blends of these. So imagine just taking a pure element like barium, and what you do is you burn it. And when you burn it, it emits some light, right? Just like any fire of any type. That light you can take through a prism, and what a prism does is it just splits up the light into its constituent parts, just like a rainbow, right? Now, when we take light from the sun and pass it through a prism, we get every kind of wavelength of light, because the white light that comes from the sun, it contains every wavelength because it's just based on the heat of the atoms that are in the sun. You have every kind of different transition occurring, which we'll talk about in a minute. So every kind of light is going to form. But what people found out is that this is not the case when you do this with elements, with pure elements. So if you take barium here and you burn it, you pass the light through a prism, what actually happens is you get a series of lines what was called a line spectrum or an atomic spectrum. And so what we can see is here, clearly this element, when we burn it, it just has these lights that can come out of it. In this case, we see a blue, blue. So maybe this is violet and blue, and then some yellows, right? 1, 2, 3, 4, 5, 6, 7 yellows, and then 1, 2, 3, 4, 5 reds. So clearly, and maybe these are greens here. It's kind of hard to tell just from this. And each time we do this with a different element, we see a different sequence of lines. So individual atoms are producing different types of light, different colors of light when they're burned, which is maybe not something that we would expect, but what do we have the right to expect anything of matter? Okay, so now how do we explain this? Well, the only way that we can explain this is by using the electrons that are present in a given element. So this is where we come up with the idea of electron energy levels. So with our atomic spectra, these lines are going to be associated with changes in energy of individual electrons. So we said before that these electrons were in like a cloud around the nucleus, but that obviously that's easy to say, but as it turns out, there's quite a lot of structure in that cloud. And that's what we're going to learn about a little bit here today. So basically, the theory here is that each electron in an atom has a specific energy level. And these energy levels are just assigned the counting numbers. So starting with the lowest energy being 1, the second energy level being 2, then 3, then 4, then 5, then 6, then 7. And as we increase in the value of n here, which is our principal quantum number, we increase the energy. So if an electron were to start in the lowest energy level 1, and absorb energy and turn in and occupy the energy level 3, well, then it would have to absorb energy to get there. It needs to get energy to go from a lower number to a higher. So we would say that the value of the energy of an electron increases as n increases. The way that we can think about it is basically think of it like a bookshelf, okay? And we have the nucleus at the center. The lowest level energy electrons are going to be as close to the nucleus as possible in the first energy level, n equals 1. Then n equals 2 is going to be the shelf above that, slightly farther away from the nucleus on average, but it has its own energy level. And then n equals 3, n equals 4, and n equals 5 being slightly farther away. Note this diagram here also shows one other thing, which I don't think comes up, but it's kind of interesting anyway. The gap between n equals 1 to n equals 2 is bigger than the gap n equals 2 to n equals 3. And that is bigger than the gap n equals 3 to n equals 4, and that is bigger than n equals 4 to n equals 5. So as we get farther and farther out, these layers get closer and closer together. So yeah, you can think of it like an onion, where the center of the onion, that first layer is the first energy level closest to the nucleus. And then as we get farther away, it's like we're peeling away more and more of the layers. Okay, so here is our theory to explain the atomic spectra that we just saw. When electrons go from a lower energy level to a higher energy level, so like n equals 1, n equals 2, they have to absorb light. So this is, we have to put energy into it to make them go up. And I said they absorb light, but this energy could come from anywhere. For example, it could come from burning the thing, right? If you add heat energy, that's another thing that the electron can absorb and then jump an energy level up. And then when they fall back down, so if they start at a high level and then fall back down, that's when they're going to emit energy. So in this case, we have a bigger gap here. So the bigger gap between energy levels means that we have, a greater amount of energy difference from this level to this level. So think about it this way. This could be n equals 4 to n equals 3. That's a small gap compared to n equals 2 to n equals 1, which is a big gap. So the bigger the gap, the greater the energy difference between the two levels, the higher the energy of photon is going to be emitted. So remember, photons, that's our word for light. So for this small energy gap, we get a long wavelength of light. For the big energy gap, we get a really small wavelength of light. Yeah, so that's an example of that. Okay, what else did I want to say here? Oh, again, you can have a full semester-long course on this because this right here is the basics for our understanding of quantum physics. Basically, electrons can only inhabit these certain energy levels around an atom. They don't exist in this cloud, like we've been saying, where they're, each position is equal to the next. Instead, it's like they have these very specific places or very specific energies that they can occupy, and they can go from one to another. So they can go from 1 to 2, 2 to 3, 3 to 5, or whatever. But they can't go in between. There's no 1.5. There's no 2.5. They have to be either at energy level 1 or energy level 2. As you can see, there's no line in here in between for them to exist at. So the electron can exist here or here, but not in between. The best way I've heard it described is comparing a ramp to a set of stairs. So like on a ramp, this is like the idea of like classical physics, where we would think an electron can occupy any level. As you go on a ramp, right, you're walking up an incline, and you can exist at any level on that incline. But that's not how nature works. That's not the way nature works. Nature is more like the stairs, where you can be on, a step, and you're on step 1, step 2, step 3, step 4, step 5 as you go up the incline. So these are the stairs, basically, is what we're trying to say. This is how nature works, basically, is what I'm trying to tell you. Okay, so let's go ahead and do some sample exercises so you have some idea of the questions I might ask you on the test about this sort of stuff. So ask yourself, for each of the energy level changes, is energy absorbed, is it emitted, or does it not change? And the 3 questions here are, what happens when an electron moves from the first energy level, n equals 1, to the third energy level, n equals 3? Is energy absorbed, emitted, or no change? How about when an electron falls from the third energy level to the second energy level? Again, absorbed, emitted, or changed. And then finally, what happens when an electron moves within the third energy level? So go ahead, pause the video, think about what we've been talking about, and see if you can come up with the answer. So pause. All right, we're back. Let's go ahead and take a look. When you go up in energy, like in A, so you're going from 1 to 3, the electron has to absorb energy to get there, because n equals 3 is higher energy than n equals 1. When it goes from n equals 3 to n equals 2, well, you're going from a higher energy level to a lower energy level. The only way to do that is by giving up energy. So you emit energy. And then finally, when an electron moves within the third energy level, there's no change in energy. It's like moving it on the bookshelf. There's no change for that energy level. Okay, so now let's go ahead and talk about electron arrangements. So let's look at the pattern of how electrons arrange themselves with regard to energy levels for the first 20 elements. So the way that we can think about this is we're going to look at the first 20 elements, and we're going to add up their electrons and then see, how they slot themselves into these various energy levels. And let's see if we can figure out a pattern that emerges. Okay, so hydrogen easy enough, right? Atomic number 1. And that means that for a neutral atom of hydrogen, it has 1 proton and how many electrons? 1 electron. 1 proton, 1 electron. Okay, so easy enough. What's going to happen is the electron is going to slot itself into the lowest energy possible. And as we talked about that's energy level 1. So there's 1 electron for hydrogen in the n equals 1 energy level. Helium, 2 protons in the nucleus. For a neutral atom, that means 2 electrons. Check the energy levels. It turns out both of them slot into energy level 1. Okay, not too bad so far, right? Okay, well now we get to the complicated part, because lithium has an atom of lithium has 3 protons in the nucleus. So a neutral atom is going to have 3 electrons. 3 electrons, we know the first 2 slot themselves into the energy level 1, but then we have a third one. And as it turns out, it doesn't fit in energy level 1. Energy level 1 is full with 2 electrons. So that means that next one has to go into energy level 2. Okay, let's keep going here. So beryllium now has 4 electrons. 2 of them go into energy level 1, 2 into energy level 2. Okay, finally, boron. Boron, a neutral atom of boron, has 5 electrons. The first 2, of course, go into energy level 1, just like everything else. But now the third fits into energy level 2. So clearly there's something different between energy level 2 and energy level 1. Energy level 1 can only fit 2 electrons, but energy level 2 can at least fit 3. So let's see how far it goes, right? So we go up to carbon, that has 4 in energy level 2. Nitrogen has 5 in energy level 2. Oxygen 6 in energy level 2. Fluorine 7 in energy level 2. And neon 8 in energy level 2. Now take a look at the periodic table. What happens after you get to neon? Where is neon on the periodic table? It's in the noble gases, right? So it's on the far right-hand side of the periodic table. And that means after you get through neon, you start all the way back over on the left with sodium. Well, as it turns out, this isn't random. This isn't like just for no reason. It turns out that the reason that you do that and you start all over again with sodium is once we fit that 8th electron into energy level 2, now energy level 2 is full. So energy level 1 was full with 2 electrons. Energy level 2 is full now with 8 electrons. So now this 11th electron that we have from sodium, that's going to fit into energy level 3. Okay, so easy enough. That goes into energy level 3. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur. We're just adding up 1, 2, 3, 4, 5, 6 electrons in energy level 3. Then we move on to chlorine and argon, 7 and 8 electrons in energy level 3. Now, where's argon on the periodic table? It's in that noble gas column again, right? So now we're going to go all the way back over to the left side to get to potassium. Why is that? Hopefully you figured it out by now. That means that we're into energy level 4. So potassium and calcium now add 1 and then 2 electrons to energy level 4. Okay, so let's look at some of the patterns that hopefully we figured out as we were talking through it there. Okay, so hydrogen and helium, they have 1 and then 2 electrons. So the electron arrangement, so okay, sorry, I guess I should start over. When we talk about electron arrangements, this is like a particular type of problem I'm going to ask you to do on the test in the future. And basically what it is you're going to take the electrons that are energy level 1, that's the first number that you write. Then you do comma, the number of electrons that are in energy level 2, followed by comma, the energy level, the electrons in energy level 3, et cetera, et cetera. So that would be like, for example, carbon we know has 6 total electrons. 2 of them will fit in energy level 1. So we start with the 2. Then the other 4 fit into energy level 2, which as we know can fit up to 8 electrons. So we'd say the electron arrangement for carbon is 2, 4. Once we get into the period 3, we are now filling the third electron energy level. So like sodium, for example, has a full energy level 1. It has a full energy level 2. So it's 2, 8, and then the 11th electron goes into energy level 3. So that's 2, 8, 1. That's the electron arrangement for sodium. And then finally, we get to potassium and calcium. And for potassium and calcium, we filled up energy level 3. So now we're ready for energy level 4. So potassium, for example, is 2, 8, 8, 1. So it's filled 1 through 3, and then just 1 electron in energy level 4. Okay. Now, what's really interesting is once we get beyond 20, the next 10 electrons actually fill into the third energy level. This is when we're in what we call the transition metals, right? Take a look, scandium to zinc. That's that little interior group there of the periodic table of mostly metals. And we don't talk a lot about those metals in this class because they don't really affect biology too much, and that's kind of where we're focused on. But what happens is once we fill the first 2 into the 4th energy level, the next 10 electrons actually fit themselves back into the 3rd energy level for very complicated reasons that we're not going to explore in this class. So down here, this will give you an idea. These are the total number of electrons that are possible in a given energy level. So energy level 1 can fit 2, 2 can fit 8, 3 can fit 18, 4 can fit 32, 5 can fit 32, 6 can fit 18, and 7 can fit 8 so far. Theoretically, level 5 could fit 50, 6 could fit 72, and 7 could fit 98. But realistically, electrons can't get high enough in energy to actually fill those in. Again, very complicated reasons. Stick to the basics for this, because this is as much as we really need to care about. Okay, so go ahead, give me the electron arrangements for the following elements. We've got carbon, silicon, sodium, and nitrogen. And I know we just looked at them on the previous slide, but I'm asking you, don't look at that. Look at your periodic table. Look at the periodic table and try to come up with the electron arrangements based on what we just learned. So go ahead, pause the video. And when you come back, we'll look at the answer. So pause. Okay, we're back. So carbon, atomic number 6, has 6 electrons. The first 2 slot into energy level 1, and then the next 4 are in energy level 2. So it's 2, then 4. Silicon, neutral, has 14 electrons. So that's 2, 8, then 4. Sodium has 11 electrons in a neutral atom. So that's 2, 8, 1. Nitrogen has 7 electrons in a neutral atom. That's 2, then 5. Okay. Oh, brief connection here. This is kind of a non sequitur here, but we talked a lot about electromagnetic radiation, and it turns out, UV light, while it can be really problematic if you get like sunburns and skin cancer and all that, if you don't get enough of it, then you can also have some problems with your hormone regulation. This is what's known as seasonal affective disorder. Southern California, we don't have to worry too much about this. This is more in like the northern latitudes, where as the Earth tilts away from the sun, you don't get as much direct sunlight. I guess it happens if you're like in quarantine as well, if you're inside all the time. You need some sunlight to kind of help regulate your hormones. And yeah, the seasonal affective disorder is supposedly the result of a decrease in serotonin when you have fewer hours of sunlight, or if you're not getting enough sunlight. And this is an example of a light box that people use to kind of like make up for that lack of sunlight. Okay, so now we explored the electron arrangement, and hopefully you kind of noticed here as we were talking about it, the electron arrangement is what affects the periodic table, right? Whenever we got to the noble gases, that's when we had a full energy level. And then once we were full, we had to go back all the way to the left. And so we return to the other side of the periodic table and start over again. So that's the whole idea of a periodic table, is we go from left to right and then periodically repeat. Okay, so as it turns out, some properties actually have patterns with this arrangement of atoms on the periodic table. And we're going to talk about atomic size, ionization energy, we'll explain, and metallic character as they relate to the way that atoms are arranged on the periodic table. Okay, so I guess, okay, we already kind of said this here, right? Oh, here we go. Okay, so let's compare elements that are in a particular group. So like group 1A, for example, would include lithium, sodium, and potassium. Now, what do these all have in common? Well, of course, they have a lot of physical properties in common, where they're very soft, malleable metals. Of course, they're metals, so they have good electrical conductivity. They're extremely reactive with water, and they burn very brightly. But what kind of chemical properties do they have, or what kind of electron properties do they have? Well, lithium, sodium, and potassium all include, filled energy levels followed by a single electron in their outermost energy level. So for lithium, that's energy level 2. For sodium, that's energy level 3. Potassium, that's energy level 1. So that's this outermost electron. They only have one of these outermost electrons, and that seems to influence why they're in the same group together. Group 2A is similar, where the outermost layer contains 2 electrons. So for beryllium, that's 2 electrons in energy level 2, magnesium, that's in energy level 3, and calcium, that's in energy level 4. So as we go down the periodic table, we can see something that these groups contain atoms that have similar electron arrangements, where their outermost layers contain the same number of electrons. And of course, we can keep going here. Group 3A, which would be boron, aluminum, gallium, similar with 3 electrons in the outermost energy level. 4A has 4, 5A has 5, 6A has 6, 7A has 7, and then 8A, the noble gases, have a filled outermost level. Now, for helium, of course, that's only 2, but don't worry about that. We know that energy level 1 only has 2 electrons in it. So helium is full, neon is full, argon is full, krypton is full in the outermost layer. So we give these outermost electrons a special name. We call them valence electrons, because as it turns out, these outermost electrons, those are the ones that are going to be given up the most easily, and it's also where electrons are going to come in the most easily. So sure enough, that affects the chemical reactions that a element can do. So the group number, in this case, the 1A to 8A, specifically will give you the number of valence electrons in those representative elements. So for example, group 7A, we just said, fluorine, for example, has 7 electrons in energy level 2, chlorine 7 in energy level 3, bromine has 7 in energy level 4. Each of these 3 has 7 valence electrons. That matches their group number, 7A. And this is going to become important when we start talking about ions and stuff. So the group number is going to tell us the number of valence electrons for those elements. And keep in mind, this is for what we call the main group elements or representative elements. It does not work for the transition metals. So we're skipping over that transition metals interior of the periodic table. Don't even worry about it for now. But yeah, sure enough, group 1A has 1 valence electron, 2A, 2, all the way down to 8A with 8 electrons, 8 valence electrons. Okay, so for the following elements, tell me the group number and the number of valence electrons for each of the following elements. We got strontium, argon, and silicon. Go ahead, make sure to use your periodic table. I'm not expecting you to memorize where these are on the periodic table, but go ahead and use your periodic table to determine first the group number, then the number of valence electrons. Go ahead, pause the video, and when you come back, we will have the answers for you. So pause, and here we go. Strontium is in group 2A, so there's 2 valence electrons. Argon is a noble gas, it's in group 8A, so that's 8 valence electrons. And then silicon, group 4A, has 4 valence electrons. Okay, so these valence electrons, as I mentioned, are really important. So we want to have a way that we can conveniently represent these valence electrons so that in the future, when we're showing chemical reactions, we have an idea of where the electrons are coming from or going to. And that brings us to a Lewis symbol. So the Lewis symbol is named after Gilbert Lewis, a famous chemist. He wrote a very important, basically general chemistry book in the 1920s, I want to say, that's still really good even today. And this Lewis symbol is just going to be a way that we can conveniently represent the number of valence electrons that an element has. And how it works is we just have valence electrons written on the top, bottom, and both sides of the element. And what we do is we specifically represent the valence electrons. So for example, aluminum, that's element 13, that has an electron arrangement of 2, 8, 3. In other words, it has 3 valence electrons. So what we do is we represent the 3 valence electrons by doing 1, 2, 3 dots around the outside. Now, note we don't pair them up. We're going to put 1, 2, 3, and 4 here. The way you can think about it is for any given symbol, think about it this way. You've got your 4 sides of it, and then each of these sides can hold 2 dots. So we're going to start by putting 1 dot each in each of the 4 sides, and then we'll pair it once we do that. So note, it doesn't really matter which sides you pick, usually I'll show you the way I draw it. Like, so for example, carbon, I like to draw it like 1, 2, 3, 4, but that's literally just personal preference. You can choose to put them in any order that you like. Magnesium with 2 electrons, you can have it top and right, top and bottom, etc. It doesn't really matter. Okay, so, but what is important is that you don't pair it up until you get to your 5th valence electron. So like nitrogen, for example, has 5 valence electrons. It's in group 5A. So we're going to do 1, 2, 3, 4. Now all 4 spots are taken up. So we put a 5th one just as a pair. Just to give like the final example, like fluorine, for example, we know there's 7 valence electrons. So there's 1, 2, 3, 4, 5, 6, 7. And that's how you would do it. Again, make sure to put all 4 before you start pairing. Okay, so now let's get some practice. Give me the Lewis symbol for each of the following elements. We have chlorine, selenium, and potassium. Go ahead, pause here, get your periodic table out, and show me the Lewis symbol for each of them. Pause. Did you get it done? Are you still waiting? Okay, let's just go, and hopefully you took some time to practice it. For each of these here, chlorine has 7 valence electrons. So it looks just like the fluorine that we just drew. 1, 2, 3, 4, 5, 6, 7. Selenium is in group 6A, so it has 6 valence electrons. 1, 2, 3, 4, 5, 6. Potassium, group 1A, just has 1 lonely valence electron. Goes right there. Okay, so now let's go ahead and talk about some of the properties that vary with the position on the periodic table. And we're going to start with atomic size. So atomic size is basically the distance from the nucleus to the valence electrons. Those are the outermost electrons. And as we go down a period, as we go down a group, it makes sense that, lithium, for example, has valence electrons in energy level 2. Sodium is in energy level 3. Potassium is in energy level 4. It makes sense that, as the onion gets bigger and bigger, the outermost electrons are farther away. And so the size of the atom actually increases as we go down a group. Unfortunately, so that makes sense. Going down a group, we get a bigger atom. So atomic size increases as we go down the group. However, it's not like what we would expect as we go left to right across the period. You might think, oh, we're adding in extra electrons as we go from left to right across a periodic table. So maybe it's going to get bigger. That's not the case at all. In fact, it's opposite. The atomic size actually gets smaller as you go from left to right across a period, to the point where the size of a fluorine atom is about half that of the lithium atom that starts the period. And there's an important reason for that. As we go from left to right, we're adding electrons to the same energy level. So there's the same distance from the nucleus. But what else changes left to right across a period? The nucleus changes too, right? So we're adding in protons to the nucleus. And as we add in protons to the nucleus, that increases the size of the positive charge in the nucleus. And that's going to pull those electrons even harder towards it. So for the representative elements, atomic size increases as you go down the group and decreases going left to right across a period. Okay, so go ahead, sample exercise 21, pause here. Given this, identify the larger atom from each pair. Is it potassium or lithium, sulfur or silicon, and then potassium or bromine? Go ahead and give it a shot. Pause the video, and when we come back, we will take a look at the answer. Okay, so potassium versus lithium. Potassium is bigger because it's lower on the group in the same group. Sulfur or silicon, silicon because it's as you go left to right across a period, it decreases. So sulfur should be smaller. And then potassium or bromine or calcium or bromine. Either one works. Calcium or potassium is going to be bigger because atomic size decreases as you go left to right across a period. Okay, So that's atomic size. That's our first periodic property. We call them periodic properties because they vary according to the position on the periodic table. Ionization energy is next. Now, we haven't talked about ions yet, but you probably have heard the word ions before, and ions are simply charged atoms. In order to get a charged atom, what you have to do is you start with your neutral atom, add some amount of energy, and that amount of energy rips off an electron from it. So this right here, this sodium, this is what's called an ion. And this is like the positive charge here. So the idea is if we add some amount of energy in there, we're going to rip off an electron. That amount of energy is called ionization energy. And the trend is kind of the opposite of what it is for atomic size. As we go down a group on the periodic table, the outermost electrons get farther and farther away from the nucleus, so it's easier to peel them off. Just because the distance between the nucleus and the electron affects the force of attraction between the two, the positive charge and the negative charge. So you're able to peel off that outermost layer more easily as you go down. But remember, as we go left to right across a period, the electrons are getting closer and closer to the nucleus, and the nucleus is getting, a greater and greater positive charge. So then it's harder to rip those off as you go left to right. So ionization energy increases left to right across a period, and then decreases top to bottom going down a period. So I know it's however you want to write this trend is the same, but you can think of it this way: it's opposite the trend of atomic radius. Because again, the farther out the outermost electron is, the easier it is to peel off. The closer in those electrons are as you go left to right across a period, that's when it's harder to. That's when it's harder to peel those off. Okay, so go ahead. We have the same set of atoms here. Identify the element in each pair that has the higher ionization: potassium, lithium, sulfur or silicon, and then potassium or bromine. Oh, sorry. Oops. Sorry. I go ahead, pause the video, come up with your answers. I'll have them up on screen in just a second. Okay, so let's take a look. Potassium versus lithium. Well, ionization energy decreases going down a group. So lithium has the higher ionization energy. Sulfur versus silicon. Sulfur has the higher ionization energy because it increases left to right across a period. And then finally, calcium versus bromine, or potassium versus bromine. It ends up working out the same way. Bromine is going to have the higher ionization energy because it's to the right of calcium on the periodic table. Okay, finally, we have the easiest one of these, which is metallic character. Now, metallic character sounds a little hand wavy, and it is. We just say, these are the characteristics of a metal, and we talk about how it varies on the periodic table. So we know. So think of things that like make a metal, right? Things that make a metal are like the ability to conduct electricity and conduct heat very easily. They are shiny. They are malleable. In other words, you can mold them into shape. These are all kind of making up for what we call metallic character. And so metallic character is higher in elements on the left side of the periodic table. That's where we have our metals. And it's lower in the nonmetals that are on the right side of the periodic table. So we can even see this really clearly if we just look at the main group elements here. For example, look at group 4A, okay? Group 4A, at the top, we have carbon. Carbon is a nonmetal. At the bottom, we have lead. Lead is a metal. So clearly, metallic character increased as we went down that period, or down that group, excuse me. Then left to right, well, period 3, for example, starts with sodium and magnesium, which are metals, and ends with chlorine, sulfur, and argon, which are nonmetals. So clearly, metallic character decreased when we went across the periodic table. And sure enough, it decreases left to right, and it increases going down. Okay, so given that, ask yourself, which of the following has more metallic character? Potassium or lithium, then do sulfur or silicon, and then finally calcium or bromine. So I'm going to pause the video. We'll have the answers up in just a second. So potassium versus lithium, we know that metallic character increases going down a group. Potassium is below lithium in group 1A, so potassium has greater metallic character. Sulfur versus silicon, well, we know that metallic character decreases going left to right across a period. And silicon is to the left of sulfur, so that means it's more metallic. And then finally, calcium versus bromine. This is easy enough because calcium is a metal, bromine is a non-metal. So you'd hope calcium has metallic character, more metallic character than bromine. Okay, and so that wraps up chapter 4. This is just the summary of periodic trends that you can use. This is directly copied from the book, so you can take this, you can just use this from your book. And that does it for chapter 4. So with this, we're going to move on into chapter 5. Make sure that you're completing the chapter 4 homework, and I believe we have an exam coming up. So talk to me about that, and I will talk to you very soon. Until then, farewell, and I'll talk to you very soon. Bye-bye.